like your whole life, and you would be happy, always passionate what you do.
Yeah, that is right.
Yes, sir. Yes, sir. It's 4 o'clock. Let's start, I guess. Is it, sir? Or should we wait for 5 minutes? Schedule, sir? Okay. So, good evening, all. We all are gathered here for the 67th webinar session of UL Space Club. And today is a really special day for us. because from the childhood itself, we all are hearing about this college. There is an upper limit for higher education.
Could you please mute your mic?
Surendran sir? Yes. So I've been talking like it's been a really special day for UL Space Club because from the childhood itself, we all are hearing about this college. And if there is an upper limit for this higher education, definitely one of the answer is go for MIT. And today, our speaker, Dr.Shikha Saini, is a postdoctoral fellow of MIT. And I warmly welcome ma'am on behalf of me and UL Space Club to our webinar series. And ma'am will be talking about the topic, crafting the materials of future, a first principle approach. And we are very happy that ma'am, you accepted our invitation to spend your valuable time with us. So we are very, very happy. And I also welcome all our other guests, our mentors, Kutti sir, Shahin sir, Shajil sir, Suresh Kumar sir, Harish Babu sir. And I also welcome all of our participants to this wonderful occasion. So without wasting further delay, I welcome Shajil sir to give an introduction about our speaker to our audience. Shajil sir.
Her findings and in the area of research, and we have people from physics and professors are there and veteran scientists from ISRO with us, along with the students and the enthusiastic students that start from the primary to the research level also. And I proudly welcome all the guests and participants gathered here. And before we go into the speakers sessions, I invite Dr. Mohammad Shahin, head of the Department of Physics, University of Calicut, to chair this great session. Welcome, sir.
Thank you, Shajil sir, respected Kutti sir, and all the senior members of UL Space Club, and all my junior friends, students, and research scholars. It's a great privilege for me to chair a session where a postdoc from MIT is giving a presentation. I'm very excited to know that she's presenting a very good topic, crafting the materials of future, a first principle approach. As we all know that first principle means we starting from Newtonian mechanics, then as we go to materials, we will see that Newtonian mechanics must be, to some extent it is okay. Beyond that, we have to take into account of quantum mechanics where density functional theory is very important. And we know that there are certain materials like in magnetism and other areas where international competition is very relevant, where the computational physics with a revolutionary approach can predict certain materials which otherwise it would be years of research in analytical chemistry and other areas. So that is the beauty of a computational approach. And we have now powerful computers which can do the extent of very long range interactions to long distance of calculations. I'm not broadening this because anyway, Shikha would be referring all these aspects in detail. And we are proudly saying that we got a very good connection from your side to our students. And without saying further, I kindly request Shikha to present the topic on crafting the materials of future, a first principles approach. Thank you. Thank you all.
Thank you, Shain sir. And without taking much more time, we welcome our proud guest to this forum, Dr. Shikha. Welcome, ma'am.
Thank you, Professor Sain. Thank you, Professor Sajil, for the nice introduction. And thank you for everyone and all the committee member of UL Space. And it's my honor to present my research journey and work with you all. And thank you for being here, for your time. So the topic of today's talk is crafting the materials for future from first principles approach. And I am Shikha. Currently, I'm working at MIT as a postdoc. And a little bit about me. I grew up in Uttarakhand in a small village, Humawala. And from there, I did my schooling and graduation. Then moved to Srinagar, Chauras campus of Garhwal University, where I did my MSc. And from there, I moved to Delhi to prepare for the JRF exam. And then I joined the IIT Delhi for my research. And from there, my research journey has been started. So the thesis of my PhD title was designing clusters for efficient catalytic activity under realistic conditions. So I got a very good remark from my external examiner. So he said, like, after a long time, I have read really a good thesis. So that was really good for me. And also, like, if you will ask me, like, what is my favorite sport at IIT Delhi? So there are the biggest stones we have there. And my spouse used to wait over there for me. And then we used to have a lot of discussion about science and also about life. And that way we end up getting the PhD degree together. And also, like, during my PhD, because I did PhD from physics department and my research tend to in the catalysis. So I hear sometimes that my research topic is not good and I won't get a good postdoc, I won't get a good position. So, but I was like always love my work, what I do. And because I learn along the way by doing my work. So, and I acquired few skills which helps me during my postdoc. And I keep on applying for the position. And after all, I got the position, first postdoc at Stanford. And there so the skill I have acquired during my PhD, those helped me a lot because I joined during the pandemic in the Stanford and I was working from home for a while. And I need to generate a lot of data set to validate my physical models. So, and so to deal a lot of data set, we should have like good skill in coding. So that helps me to do my work very fast over there. So I have developed two models. One is to predict the chemical energy on surface alloys, and another to predict the binding energies of the metal atoms on the alloy surfaces. And then from there, after 2 years, I moved to MIT last year in March. And the group of the Professor Bill Gildy's group, the group is really good in a sense that 70% of people are experimentalists and 30% people are computational. So we could have a nice discussion between experimentalists and theory computationalists, and then how to approach a problem from both the perspective, and what are the challenges in the experiment and what we can bring from the theory. So I'm working over there in a close collaboration to understand the interfaces of the materials for the application in power device and radio frequency electronics, and also in the dynamics ion transport in solid electrolytes, which has the application in battery materials. And then, so doing science also allows us to have fun. So I always love to go to beaches and to see sunrise. I go for traveling sometimes by taking off. And also I go for hiking for a while during weekends. And I love tea. I can't start my day without tea. And also I'm very interested in finance currently. So my academic journey, I have the training in condensed matter physics, computational material science, and I'm expertise in density functional theory and method development. I'm comfortable of doing high throughput modeling. And currently at MIT, I'm learning doing the ion transport using the molecular dynamics simulations. And my research interests are in surface alloys, method development, semiconductors, catalysis, ion transport, and energy storage material. So the outline of today's talk is first we will have the discussion on pillars of material science, history of materials, introduction about multimetallic alloys, key physical properties to design a model, and background and limitations of previous models, then designing the new models and their performance. So we have 4 pillars of material science: structure, how the materials are arranged in what is the symmetry, how, what are the structure and their properties and their performance. So based on properties, there would be a certain performance of a material for a given application. If for a given application, the material is not good, then we can do certain processing, we can apply, we can do the mixing, heating, boiling, and we can make another materials to have the performance that we desired. So a material science is relationship between structure, property, processing. So how the processing basically impact to designing the material. So recently I have attended the talk from the recent Nobel laureate, who the Professor Bhavandi. So he basically, they have designed the quantum dots during 1993. So he basically saying they gone down from 3D to 2D and to the quantum dots, which are the tiny particles. So by changing the process, how we design the material, then we can design the new materials, which can lead to different stream of the science. And he basically said that he didn't thought about that the application would be that huge for the quantum dots, like in medical science and in LED and so many things. But he said he just thinking of studying the materials only, and the work impacted science a lot and also the application. So which basically inspired me a lot of doing more and more science. So if we take the example, how to go through all the pillars. So suppose we need to make a house from the gingerbread. So what we need basically, what performance we need the house having the strong walls and roof. So for that, what kind of braid we need? We need a braid which have a good strength and ductility. So then what we need to do? We need to think about the structure. So butter has fat and water. So when we heat, then the water becomes steam, and it will create the air pockets in the butter, and then that could create the holes, and it will the bread would be little soft. But we do not want the soft butter, we want the strong butter. So we need to reduce the content of the butter. So now we need to see like how is the performance of our butter. So we do the characterization in the lab to see what are the desired property we have to measure. So here we will measure the stress and strain to see how much strength we have with our butter, our braids, and then we create the house out of it. So in similar way, when we go, like we do research experimentally or in simulation, we go almost around all the steps to come up with a new material. So now to see, so let's see a little bit history about the materials. So human history is the history of the development of new materials. So when humans have emerged, so first we have the Stone Age, where for our survival we use the tools out of flints and clay. And then after a certain time, when we understand like how to use the fire, then by using fire we can burn the clay, and out of it we can extract the metal. So clays are the oxide forms, and then we can burn, we can remove the oxygen, and we have the metal. So metal in clean form would be very soft, so we cannot make the tools out of it. Then the human understood that if we can mix two metals, then we can have the strong material, and then we can make the tools out of it. So here after that our Bronze Age and Iron Age has been started, and then human started settling down in our villages, and the civilization has started. And then after that we have then if we reduce the certain amount of carbon in the iron, then we have the steel, and with the invention of the steel we have the industrial revolution in the history. And then we have the nickel alloy based alloys. Then we can make the big machineries, jet engines. And then currently more recently we have the information revolution with the silicon chips. And also we know right now the AI chips has a lot of sensation to take this information revolution to the next level. So as a summary, whatever material we use, it is always in some alloy form. So we mix the materials, also to use the chips, we also make either P-type conductor and N-type. We do little mixing with the material to have the desired property for a particular application. So with that, we have different type of materials like ceramic, plastic, semiconductor, metals, rubber. Some are very hard, some are very soft. So why? Because we have the different type of bonding and different type of symmetry. And then with the given materials, then we do a lot of processing to create new new things out of the materials, like electronics, aircraft, and to materials for the defense and chips and so on. So more recently, the new type of materials have emerged, which we call alloy. So alloys has been first proposed by the Professor Kandur and the Professor Gay. They published the work on alloys in 2004.
Please mute. Audience, please mute your mic.
Yeah. So first, like in Professor Kandur lab, so one undergrad student actually synthesizes a material they mixed the 20 metals together and they did the synthesis. So they found there are the in the TAM image they could see the single crystal formation consisting 5 elements, and that time they could not understand what is that material. But later on, after few years back after, then postdoc student took the project, and then they did the experiments again, and they named that single phase crystal as a alloy, and that is named after Professor Cantu alloy. And at the same time, Professor Ye also was working, and he named them as high entropy alloys, because the formation of the single phase having so many atoms arranged randomly within the single phase has been driven because of the high entropy change, which basically lead the formation of the stable phase of high entropy alloys. So here we took different metal atoms and having the different structure symmetry, but they could create the because of the high computational entropy of the formation of the materials. Now, the another question is why still we are searching for new materials in material science, because still we have a lot of challenges in front of us. And here are the list. So on the top of the list, we have energy and the environment issue. So energy means the money. If a country can produce the more energy for their population, then the country would be more and more richer. So we need the materials, the low cost material, and the processes with using which we can create the more and more energy. We can provide the energy to the population on a very low cost. So that is the main idea, always to look for the new promising materials. So here I will talk about in speed of the catalysis. So we will in catalysis we look forward to have a material with low cost, high stability, high activity, and high selectivity, and the durability. So now, so we are looking for the alloy system. Can we design the alloys having the good performance for the different chemical reactions? So what is the catalyst? So, and why do we need the catalyst? So when a reaction has happened, so it requires certain energy from reactant to product. So the height will tell us how much amount of energy we need to provide to perform the reaction. But if we perform the same reaction in the presence of the catalyst, then there would be different steps, like adsorption of the reactant to the catalyst. Then they move around, and then they combine and then they dissolve. So we have different elementary steps during the process, and each step then will be easy in the presence of the catalyst. So we will have a different path having the low barrier to perform the same chemical reaction. So that way we can save a lot of energy, and we can create more products with using the good catalyst. So in industry, 85% process rely on the catalyst and to make the low value product to the high value products. So now, why the multimetallic alloys are interesting for the catalysis, and what we are looking for to design the best catalyst. So suppose we need a particular properties for a particular reaction to be happen. So suppose we need a certain catalytic activity for a given reaction, and we want to screen the materials which would be the best material. So we look for certain physical properties. So suppose we have the single metal catalyst. So we go from one metal to another metal and check their properties. So on this surface, all the sides would be the same. So the catalytic activity of each side would be the same. So that way we will have only limited possibility to be in this region. So we want to be in this region where the activity would be very high. So we will have the limited possibility. Now, if we have the alloys, so in alloy, so the metal atoms would be randomly arranged, and we could have the sites having the different catalytic activity, because when we change the surrounding of the site, then we change the property of a given site on the surface. So that way we will have we could have a continuous spectra by changing the morphology and the chemical environment of the material. So that way we will have we could have the many candidates which could give us the desired catalytic activity. So now further question is, okay, we have a solution, but now because now the space of the materials would be very large, because once we have like 4-5 materials in, and we combine them and we change the ratio of the different elements, and then we change the morphology and the composition, then the space of the materials would be too large, and then we have to screen like which amount would be suitable for a particular reaction. So that then again would be the challenge from the screen perspective. So suppose we have a given materials, 3D, 4D and 5D transition metals in the periodic table, and we can pick different materials, and we can mix and can check like, okay, which one is best for which reaction. So there would be gazillion proper opportunity to design the material. But if we do the screening by doing the experiment for each case, then it would be very challenging from experimental, and from the simulation also we need to do a lot of calculation. We need to use a lot of resources. So then the way forward is to have models which could basically do the pre-screening and to guide us like, okay, which composition, which chemical environment could be the best, which we can do the computation and do the synthesis then. So one question has been posed from our collaborator when we were doing the model designing, that they want to understand what would be the suitable composition for propane dehydrogenation reaction. So they are mixing the platinum, copper and cobalt. Platinum is very costly material, so they want to reduce the cost of the catalyst by incorporating the copper and cobalt in the system. So now if they do the mixing, like then how much amount of copper we should have, then what would be the stability and the performance, and then if we add cobalt, then how the scenario will change. So that those are the questions which we will answer later on. Now, so when we design the model, we pick certain properties which we call also the descriptor. When we do the screening, you might hear from the machine learning people also, they look for the descriptors. And so here for our model, we have picked the site binding energy and the chemical energy. So the work I will talk about here, we will mainly focus on the site binding energy. So it is the energy required to knock out a metal atom from the surface. And the chemical energy is the strength, how strong a surface bind the adsorbate or reactant on the surface. So now how why the descriptor or the properties, given properties are important for designing the material, because suppose here we will pick a property like coordination number, which we can just calculate by counting the number of atoms around the site. So here we have the site around having coordinated by 9 atoms. And this is the 100 surface. We have the coordination number 8 of the site, and on 211 surface we have the coordination 7. So once we change the coordination number around the site, we change the activity of the site, like we change the binding energy of the site. Here it would be the binding energy would be more, here less, and here will be the binding energy more higher, so the site would be more active. So that way the given property we can correlate with the adsorption energy. So we know that adsorption energy linearly correlate with the coordination number for monometallic system. So if we increase, so if we decrease the coordination number, we increase the adsorption energy. So for lower the coordination number, the adsorbate will bind more strongly to the surface. And also we can also knock out the metal atom around the site, and that way we can reduce the coordination number. So another property also, like the D-band center, and there is a D-band model which is very famous in catalysis, which basically, by using the D-band model, we predict that which particular material or site would be reactive for the reactant. So what is the D-band model? So when adsorbate come in the proximity to the surface, then it interacts with the electronic state of the surface. So the assumption has been made that when there will be the interaction, only the electronic state of the adsorbate will perturb. So surface state won't perturb. So that was the idea there. So adsorbate reactant first with the sp state, which are highly delocalized, and will give the renormalized state. Then this renormalized adsorbate state will interact with the d states of the metal site. And then this interaction will give us the bonding and anti-bonding states. And then the adsorption energy would be the sum of the interaction with the sp state and the interaction with the d state. So this would be the constant term because the sp state will be highly localized and they will be identical for all the metals and the alloy system. So to have the variation in adsorption energy from one surface to another, so it will be governed by this term, the interaction with the d state. So for the monometallic system, we know that the binding energy of the site correlate with the D-band center and also correlate with the change in the coordination number. So idea is that if the D-band center will shift towards the Fermi level, like the value will be less negative, then the binding energy will increase. So the binding energy will be more high if the d states are away from the Fermi level. So that way we have the, for monometallic system, we understand them well. Okay, if where is our D-band center, what is the coordination number? So by given those values, we can predict how reactive our surface would be. But when we go to the alloy system, so what will happen? So we have three scenario here. So the coordination number of the site is same in all the cases, but the interaction of the site with the surrounding would be different. So that the bond energy, metal energy for in this case would be very different than the metal energy in this case, because now the property of this metal site would be different than the central site. And if we add more atoms, different atoms around the site, then the catalytic activity for this site would be very different than these two cases. So if we change if we have the fixed coordination number for a given site and we change the surrounding, so by changing the surrounding we can change the activity of the site. So now, so one more example, if we see like where the D-band model fails. So here we have one example, like the adsorption energy of CH3 molecule on the platinum side. So we have a given adsorption energy. Now we change the surrounding of the platinum side by adding the copper. So by adding the copper to the platinum site, we shift the D-band center towards the Fermi level. So if we shift the D-band center towards the Fermi level, it should be more reactive. So we should have the linear pattern like this. But after a certain time, our curve bend off. So now we are losing the adsorption energy. So it is the contradiction with the D-band model. So what is happening now? So if you see the density of state for platinum, clean platinum site, and when we change the surrounding, so we see here we have the anti-bonding states here, unfilled state. Here we also have unfilled states. But when we add more and more copper around the site, you can see that the shape of the D band D state would change significantly.
കൊടുത്തോ എത്രയുള്ള റിസൾട്ട്
Srikumar, can you please
നമ്മളിലുള്ള ആൾക്കാർ
Srikumar, sir?
വന്ന ആൾക്കാർക്ക് 17
Srikumar sir, please mute your mic.
അസൈൽ സാർ കൊടുത്തു ബില്ല് കിട്ടിയില്ലേ
So now we are changing the shape of the D states. So now we cannot only rely on the D band. We have to take into account the weight.
എല്ലാരും വിളിച്ചോളൂ.
So we have to take into account the width of the D states. So now, so therefore, we aim to design the new approach to predict the activity of the alloy surfaces, and so idea is that we want to perform the only limited DFT calculation to design our model. And the model is based on alpha scheme. So what is the alpha? Alpha is the term bond associated energy. So the interaction between the metal. So what we will do, we will predict the bond energy with our model. So what we do, we basically create a training set where we will change the coordination number and we will of the site, and we will pick the different surfaces to have the good statistic of the coordination number. So then we will calculate the site binding energy from the given training data set, and then we will assign now we need to predict the bond associated energy, like the energy of the bond when we will add a metal atom to the surface. Then for the each bond, like we have the coordination number 4 or 9. So what would be the energy of the ith atom the formed when we add the atom to the surface? So that way, so we have the equation, like we have the parameters, we have the matrix. So the matrix would be the counting of the coordination number when we add the atoms, and our Y is the array of the binding energy from the DFT. So by performing certain DFT calculation, we can predict the metal interaction energies. So now when we have the energies, bond associated energies, so what we call the alpha parameters for a given bond. So now what we can do, we can calculate the energy of the system. So now we have the atom, how many atoms we have correspond to each atom. We can write down the energy associated with the atoms in the system, and then we have two configuration when we have the site here and when we knock out the site from the surface. So we will calculate the energy from the alpha parameter, and we just take the difference of both the configuration, and it will gives us the binding energy of a central site. So now this is the monometallic case. Now if we have the alloy surfaces, then how our training set would change. So now we will have the pairs, like suppose I want to have the alloy made of platinum and palladium. Then what I will do, I will have the training set for the clean surfaces having the different coordination number, and the site like the another site in the dilute case of the another metal atom. So we have the clean sites and we have the site in the dilute configuration. So how many calculation we will do? We will do 18 binding energy calculation and how we came across these 18 surfaces that we have to include this. So we did a lot of testing and training by including all the possible configurations on the 3x3 surfaces. And from there, we did the testing that, okay, we need the 18 DFT binding energy calculation for a given surfaces. And then that would give the best alpha parameter. And then we can predict the binding energy by changing the composition. So suppose I have 3 metal atom or 4, then I need all the given pairs like platinum, copper, palladium. So that way we will calculate the alpha parameter for the given pairs. And then once we have the alpha parameters for the given pairs, then we do the linear interpolation for our ternary cases. So now we have the site where we have like platinum or palladium 3 type of atom, and the central site is ruthenium. So that way we could how now we have site. Now I will randomly change any composition. So I could have any number of so here we have platinum, palladium, ruthenium. So we have a central site. Now I will change any given number, palladium, any number of ruthenium, any number of platinum. So I am changing the configuration, and by changing the configuration, how the alpha parameter will change, because I do not want to train the alpha parameter for each given configuration. I just had the for clean and the completely dilute system. So what is the scenario here? We have the assumption that if we change the composition linearly, so we can do the linear interpolation for our alpha parameter. So that way we can have the alpha parameter for a given composition. So now we can define a given site. We can define the energy of a given site in terms of the alpha parameter for any random configuration. So now I have the alloy surface. So the same thing I will do. I will calculate the energy of all the given metal atoms, and I will do the sum for to calculate the energy of my surface, and I will knock out the metal atom and I calculate the energy. So what I need to do, I just write a script and then immediately, like within few seconds, I can have the energy of this system, I can have the energy of this system, and I will just take the difference. So I immediately can have the binding energy. So now we need to check the performance of our model. So how well it can describe the different cases. So we did testing on lot of data set. So here I'm showing only one case, iridium, ruthenium. So we have designed the different surfaces, 1 surfaces, 1 0 0, 2 1 1, and also the nanoparticles also. So I created a lot of random configuration and calculated and the binding energy from DFT also and from the model also. And then here we see the binding energy calculated from the DFT and predicted from the model. So we can see the mean absolute error for our prediction is 0.15, which is a reasonable accuracy we could have from our model. So how many number of parameters we require. So suppose we have the alloy system having n elements in the alloy system, then it requires n square total alpha vectors. And then how many binding energy we need? So we need 18 times n square binding energies to calculate from the DFT to train our model. So we need only a limited amount of computing resources, and then we can screen the large space of the alloy surfaces. So suppose I create a big nanoparticle having more than 3000 atoms, and I want to calculate the binding energy of each elements on the surface. So what I will do, I will just run my script by giving the structure of the nanoparticle, and immediately I could have the the result, that I can see, okay, so how much is the range of the binding energy spectra I have for the ruthenium, for platinum, and for palladium. So now what we need to look, like, okay, so we have a spectrum of the binding energy for a particular site. Now for a given chemical reaction, which range I need to pick. So we have a linear scaling relationship from where we can linearly scale the adsorption energy of a given reactant with the binding energy. And from there, from this linear relationship, we can see, okay, which region we should target to have the binding energy for a given adsorbate. So that according to that, I can tune the amount of the platinum, palladium, and ruthenium atom, so that the statistics should lie in a certain region. So now further, what is the limitation of our model? So right now the limitation for the model is that the metal atoms we are picking here, the lattice parameters should be very close. So if the lattice parameter would be like the difference in the lattice parameter of the atoms would be large, then there would be a lot of strain within the system, and there could be like, we could see the bond are breaking, maybe on the surfaces or nanoparticle, or maybe particle are not stable. So they're like having the lot of strain may on the system will induce lot of error on the model. So therefore, for the strain system, we further need to basically improve the model system. So now we basically, from our given model, we want to give the answer to our experimental people. So here, when we do the mixing of the platinum and copper, so here we can see that this is the clean platinum side, this vertical bar, and this is the copper binding energy in clean surface. So we can see that the binding energy shifting up means like we have the higher binding energy, means site is more active, and the copper site are more stable. So inducing copper, giving some stability to the alloy, and also giving the higher activity to the platinum side. But okay, we have the high activity here, but the problem was in experiment that at high temperature, they could see that the alloy is not very stable. So they could see the distortion on the particles. So they now want a more stability of the alloy system at a higher temperature. So that's why they want to add the cobalt and want to see the effect of the cobalt. So when we will add the cobalt, how much cobalt we should add to balance our platinum copper alloy? So copper anyway will reduce the cost very significantly. Now the issue is to have the good stability. So when we add the cobalt in a very large amount, then we lose the activity of the site. So it will make the system more stable, site become more stable, that we do not want. So when we have the all three atoms in the same ratio, then the activity is reasonable for our platinum sites, and also the stability also good at high temperature when they perform the reaction. So that way we could see, okay, like where our spectrum is lying and how much statistic we have the on our active site and on our like less active site. So that way we could answer the question from our model, and also like we also like predicted more alloy surfaces for other chemical reactions as well. So now I would like to thank to my peer, the PI at Stanford, that for the work I have shown. So here, like I learned a lot from the theoretical perspective, how to design the model, what shortcoming of the previous models, And I would like to thank to my current group members for the discussion and for the opportunity to work at MIT, and also the computing funding and the computing resources we have here. And thank you everyone for your kind attention, and I'm happy to take any question.
Thank you, Shadil Mash. Oh, it has been a very, very, very nice afternoon to listen from Dr. Shikha. An excellent talk on a topic which we have not so far handled on materials. It's a very, very nice one, and particularly we are listening it in the afternoon, and she is there in the early morning in US. And giving us the excellent opportunity of listening to a topic of contemporary interest as well, and scientific interest apart. And I wanted to say that, you know, the dream destination of the students, particularly in science, is the place where you had been. IIT, Delhi IIT, then you moved to Stanford, then from there to MIT. This, your route, is of exceptionally important thing for our students to note. That is our dream destination, their dream destination. You have been able to reach there, and it is. I'm sure that they get a lot of inspiration from you, having achieved this kind of an academic excellence in your journey globally. So we are very, very happy, excited to have a person like you to address our students and the veterans who have been here listening to you. Thank you very much. And I don't know how to thank you for your great contribution to our UL Space Club in agreeing to come here and spending your valuable time with us. Thank you very much.
Thank you so much.
Oh, thank you very much, Shikha, for wonderful presentation on your research work. Maybe I know that a lot of questions are awaited in the chat box. Let us start one by one. Maybe who can read it, and so that Shikha can answer them. Who will volunteer that, please?
Sir, there is.
Yeah.
Yeah, Dr. Shikha, your talk is very illuminating.
Thank
And
you.
I think definitely students will be highly enriched of your basic insights in how to get into the material characteristics in hold. Can you just clarify for the benefit of audience as well as myself? There are two questions from my side. Is there any basic simple model for a classroom students like engineers, which they can use it and run to understand the coordination number and try to characterize simple models if they are available that you can maybe highlight. The second question is, if I wanted to look for a material, for example, in our space systems and all, when we put a high pressure hydrogen or any kind of a liquid fuels, we generally pipe it through multi-layered pipes. In fact, the conduction, the temperatures will release the material because of the diffusion. Okay. Now, in such situations, if we do not want the loss of my liquid propellant, which is being, of course, so even the Elon Musk must be doing the same thing. How do we minimize and optimize the material piping suitable for such kind of things? Just a kind of pushing the limit of thinking. We wanted to know these two things.
Okay. So for the first question, for the coordination number, if I can provide the script, and there is one there are like environment, like I use the ASC environment for to design my scripts easily. So, but there are there are already script like to have the coordination number. You can explore the GitHub. When I need to see some, like what I want to go around some script and I want to start. So sometimes I go around the GitHub by Googling, like if there are some script which I am looking for, and I will modify it according to my desire. So one way is to look on GitHub also, and and also ASC environment is really good, which I use, and also for designing the material. So to have the less diffusion. So basically we calculate the barrier for how will be the barrier to breaking the bonds. So similarly we could have the from this model as well, but it is limited only for the alloy, like the metallic alloys. It is not compatible with the oxide system. But if we calculate the diffusion, so suppose we calculate the diffusion barrier. So like I'm calculating the diffusion diffusion barrier for migration of lithium from going one place to another. So if barrier is huge for diffusion, so then in a very harsh conditions, our material won't degrade. So we should have a high barrier if we want for the diffusion, if we want a very stable material. So, and also like if then another thing is like mixing. So suppose we have a material which we were using and it getting degrade. Then what we need a more stability. Then we need to pick like, okay, what kind of material we can add, which basically provide the more stability for that can sustain to the harsh condition as well. So I think by having some model which can predict the diffusion barrier easily, how fast they are migrating. So even we can provide some like we can do that.
Why I asked this kind of thing is, of course, there is some hind requirement. See, entire tropical world experiences extreme heat. Okay.
Yeah.
Now, if the building materials, if they are probably with a less conduction losses, appropriate material with a lightweight, probably this would go a long way into the developing nations. That's all. That is the idea. Okay.
Yeah. True.
Thank you. Thank you very much. Yes, sir. Shajil sir.
Yes, it was a very nice talk, but of course, I could get a lot of insight into the materials. Thank you, Shikha, for the fine explanation and then the nice examples which you have given. It really has given me some idea now about otherwise. Basically, I'm not a material science person. I'm from space dynamics kind of a thing. It has given a very good insight into it. Thank you very much for your valuable, informative talk. I hope the students will be very much benefited. I don't want to stand in between you and the students. Thank you so much.
Okay. Thank you, Shikha ma'am, for a wonderful lecture. So now I welcome Eleonora to handle the question answer session. Eleonora, are you here?
Yes, I'm here. Hello, everyone. Good evening. So it's time to start our Q&A session. I have taken some questions from the chat box that you have texted. So if you have further doubts, you can post in the chat box along with your name and class. So, ma'am, I'm going to the first question. It's from Archit Iya. Which material we will probably use to build a Dyson sphere or a Cooper station, which is shown in a movie called Interstellar? These structures are huge and the material we use should be very less in weight, easily available in our solar system, and it should be very strong. Is there any material like that?
So you want a light material, right?
Yes, I guess.
Yeah, it should be light and very strong. And it should be easily available.
So yeah, so very like, so when we go to the periodic table, so we can have like which elements would have the like the last coordination number, and also the cells would be, for stability, the cells would be mostly half filled or full filled. So we can have the idea from there. So I think in our case, like copper is the light, like the very cheap material. I think I would go with carbon, I would say.
Something like carbon fiber.
Yeah, I would go with carbon, like something made of carbon.
Okay.
Yeah.
Carbon is fast. Is found easily in solar system, so it's a nice choice that we can choose. I can't hear you. I can't hear you. Okay. Actually, my name is Archit, and I'm from Kozhikode. I'm studying in 8th standard, and I'm studying in a school called Ayathan School. So, about my hobbies are stargazing and reading books. Or I have globe, so I'll search a random space in the globe, and I'll learn about it. So there are coordinates, right? And I'll code. Nothing. That all much, and there are no hobbies like that, so it's all about me.
Okay, sir. So the next question is from Adidev. He's studying in 7th grade. Ignoring the cost limitations, what would be the best material for a pressurized container like a commercial aircraft or rocket hull, balancing strength and weight perfectly?
So I think for the aircraft material, so I think from the strongest perspective, I think the hardest material we have the diamond and cubic boron nitride. So first is the diamond, and the thermal stability is highest for the cubic boron nitride.
Okay, can I proceed with the next question?
Yeah.
It's by Adil Prajesh. He's studying in 7th standard. He's asking that which is the common metal in the earth?
So the common metal. I think all the metals are common. All the metals are precious. We need all of them in one way and another. So in terms of abundance, what we have hydrogen, lot of hydrogen atom, and if we go to the metal, So I need to think which metal we have more in terms of percentage. I don't have exact answer, but in terms of an abundance, I think we have hydrogen, a lot of hydrogen and nitrogen.
He have one more question. Which is the last metal discovered?
Sorry, I don't remember.
So the next question is from Abhinand Krishna. Which is the most expensive alloy for this process and what are its advantages compared to other alloys?
So the if we go to the actually periodic table, so we basically want for catalysis we want to be in among the 3D, 4D, and 5D series. So among them, the costly material is platinum, palladium, rhodium. So these are the very costly materials in terms of, you will say, the cost. So we want to but they are really good. So suppose in certain chemical reaction, platinum is the only person to go with. So in terms of the performance, then so the only way forward is that we could mix the platinum with other metal atom or platinum, we can say the rhodium, so that we could reduce the amount of the platinum and could have the activity, the same activity or higher activity. So that is the idea.
Okay, ma'am. Adidev, I have one more doubt. That why can't carbon fiber be used for undersea vessels like submarines?
Carbon, okay, so actually with carbon, the good thing with carbon is like with the material itself. So if I go with here, my slide here is, so yes, so here. So actually, recently I am working with diamond and cubic boron nitride. So this is basically I'm working to make the radio frequency electronics device and also in the power devices. So main purpose to studying is for the aircraft, for the space craft application, so that we could have the devices which can sustain the harsh conditions. So that is the idea, and we could have the high mobility. So the beauty with the carbon is that it can be diamond, it can be graphene, it can take another forms as well, right? So the thing is that with the material, that how you are like designing it, how is the atoms are arranged, what is the symmetry. So in diamond it is so dense, in such a very good symmetry that it gives us such a good stability and hardness. So similarly, and then we can the same carbon atoms we can arrange in different way with our like own desire, so that we could have the different stability, different properties. So I think that could be the reason that we are using the carbon for that purpose.
Okay, ma'am. This question is from Devananda Srijit. She is studying in 8th standard. What is the concept of grain structure in metals and its impact on material properties?
Grain structure, you means grain boundaries?
Yes, ma'am.
Yeah. So yeah, that is a good question. So basically, actually, I was not familiar before for this because I was just working on surfaces. So currently, I'm working on this battery material, so electrolytes. So right now, I'm just working on bulk, but we have in the collaboration we have a lot of discussion on grain boundaries. So in grain boundaries, what happened? Like we have the different cut. Like okay, we different facet 1 1 1 0 0, and when they like in a system, we could have the interfaces. And then that we call the grain boundary. So what happened on the grain boundary? So when you have the different facet or like combining or at the interface, so what will happen at the interface, we could have the different type of strain at the interface, and the local structure will change at the boundary. So in certain cases, like in electrolytes, so what happened if usually their grain boundary would be there, like when we synthesis there could be a lot of things, but when we design from computationally, we can design those, but our model system would be a little bit ideal, so from what we have in the experiments. So then what will happen, so at the grain boundary we could have the higher conductivity, and in some case we could have the lower conductivity because of the formation of grain boundary. So if so what happens, so suppose I would give example. So in one type of material like garnet, so what happen when an atom migrate from one side to another, so there is a combination of structure, like we call the bottleneck size. So what will happen through this bottleneck, one atom will hop from one side to another side. So suppose at the interface, the bottleneck size is reducing. So you are reducing the space to migrate, to diffuse one atom from one side to another side. So, and if your grain boundaries are formed in a way that they are making more space to transport the atom, so we could have more diffusivity also. But it depends on the given system, what kind of system you have, and what kind of local mechanism defining the diffusion of your given conductor. So yeah, it depends. It will vary from metal to metal. So my goal also, like we don't understand garnet yet very well, right? What is the matter when we will apply the strain, when there will be the grain boundaries, because at the grain boundary different type of strain also will be there. So when we say the strain, so at grain boundary there could be the different scale of strain or stresses than the bulk region. So at the local structure will change, and how local structure will change, and how the dynamics will associate with those changes. So that is the whole, like also we want to understand that as well. Yeah.
Okay, ma'am. Thank you.
So
Shakira, I think Professor Pradyumnan is also in the meet. He's not, I don't know. Okay. Okay, then it's okay. I have a small question. Considering the demand of energy materials, what is the future of high throughput calculation for replacing lithium? Do you have any idea, Shikha, please?
So yeah, so one thing is basically actually this thing. So one is like we could have the higher conductivity, so we can explore the lithium base. So right now I'm basically focusing on garnet. So another thing is actually I didn't explore another electrolytes, lithium based electrolytes, but recently I was listening the lecture from the talk from Elon Musk. So he basically saying that they are trying to focus on sodium based electrolytes, sodium based batteries, because they can reduce the cost of the battery materials. And but there would be, like he was saying, then the only thing is that we need to the charge, like the lithium battery will last more longer, we can drive more longer distances, but with that we might need to recharge more often with sodium battery. But we can reduce the cost very significantly if we will use the sodium based electrolytes. I'm also interested like which kind of sodium based electrolytes they are gonna use in their manufacture. They might using, because if they are saying they might be using. So yeah, but right now I'm basically focusing on lithium based electrolytes only, because the garnet. So yeah, one question I also want to mention here, basically what I learned here. So this garnet electrolytes, they are disordered. So if we have the order system, we will have the limitation of the migration, but it may be in disorder based structure where the lattice itself having the random configuration of the lithium. So that could give higher active conductivity. And in this case also, like in lithium, so Garnet, what happened if we will create vacancies of lithium and we'll add another dopant in the system, then we could, and we do the lithium vacancies, we make more lithium sites available to migrate and hope. So then I think that is also one possibility, that we took a disorder system could have more activity and we mix the systems so that we could reduce the cost. That would be the one thing if we just want to go with lithium based batteries.
Okay, thank you. Thank you.
Yes, sir. Sir, how much can I ask in most? The next question is from Ritvik. Has material science helped enhance the performance and efficiency of electronic devices such as batteries?
Yes. So we can so that is the idea, like here. So one thing is always like creating, as I mentioned, creating the defects in our favor. So when we do the synthesis, we always will have the defects, or when we add something, we call like, okay, we are creating defects or we are allowing. So so in this case also, like because we want the transistor out of these interfaces. So I want the higher conductivity, higher mobility. So okay, so I do not want the defects which will harm my system. So I want, so, and when we modify the system basically, so we are creating defects even in electrolyte battery materials also. We are creating defects to get the more conductivity, more ion transport. So there could be some defects which can harm the system, like our conductivity. So sometimes we need to change the environment, like the conditions, experimental conditions. So maybe like suppose some growth condition will suppress certain defects in the system, and will create, then we can tune, if we know, okay, if I will create this defect, so when I will we are discussing with the experimentalists, they say like, if we know like, okay, by creating some defects we'll create more mobility in the system, conductivity, so then we might can control the synthesis part to have those defects in our system. So I don't know how they will control, but they are saying. So, and in the same way, like we can modify. So there are like this like, I think the growth condition, how you are basically synthesis the materials, it's really impact a lot. Like so one inspiring thing when I was listening the lecture from Professor Boundy, so he was saying they could see the quantum dots in their experiment when he was the postdoc, but when he was the faculty at MIT for 3-4 years, they could not detect the quantum dots because the process they were taking, there was some mistake. They have to create the environment air free when they are making the dots. So after certain times, like 3-4 years later, losing a lot of money on the synthesis process, and then they figure out, oh, they have some mistake in their synthesis environment, and then they fixed it, and then they could see the quantum dots. But still, then there were more challenges, that all the quantum dots are not good, they are trash. Then they again change something. So when we design the material, so and we start doing the process, then maybe sometimes we will fail, sometimes when we understand this is the problem, we have to fix this, and then we will fix it by changing the environment, or by changing the morphology, or by creating more defects, different type of defects, or adding the dopants in the system. So that there are like lot of possibilities. So if we will not explore, we won't be able to create more or to understand more about the materials.
So, ma'am, can I ask us next question? It's from Vishwajit. He's studying in 10th standard. What is the best metal or alloy which is easily weldable and can withstand high pressure and has strength?
So high pressure. So I think then I need to think from the metallurgy perspective. So I think I exactly don't know from the the data set, but I need to check because this professor what is where is this? So yeah, so when they created this this alloy, Cantor alloy is 3D 3D transition metal atoms, and they are from the metallurgy department. So their focus is to create the metal for which have the good stability. So I think I think 3D transition metal based elements would be maybe good for the high strength. But I'm not sure. I need to check for that thing.
Professor Libu, you have something to say? Libu Alexander? No. Okay. Okay. Over to Shadil sir. Then.
Sir, one more question. The last question is from Rifa Fatima. What are the peculiarities needed by a metal or element or compound, something like that, to be the best catalyst?
So, for from the catalyst perspective, okay, I will say one thing here. So suppose so best in terms of what? In terms of which reaction? So suppose I'm creating the platinum based alloys, right? So they are good for the dehydrogenation of the alkane. So for alkanes compounds or reactants, we should have the platinum in our but maybe for for HER, OER, maybe there are like different type set of materials. So basically the idea is uh, in catalysis, so this Sabatier principle. So your reactant should not bind so strongly to the surface that it won't dissolve, right? It should not be so strong to the surface and not so weak. So we need the balance, like we need somewhere in between. So it will depend. So is catalyst is best or good or bad or good? So it will depend on the question, like which reaction, for which reaction you are looking. So might be for ammonia we need different catalyst, maybe for hydrogen HER we need different, because it will depend like what, how our this volcano, like we like our adsorbate is reacting with the surface. So for different reaction it could be different, but the idea is that it should the binding energy should be very balanced on the surface, that it could easily dissociate or adsorb and then react to another molecules. So that is the whole idea.
So it's time to conclude our Q&A session. Is there anything to add, Shelsa?
really nice. I really like it.
Really, I'm here because I am a little late for hearing this talk. That is why I'm not asking more questions. But anyway, I found that all the questions asked by our students very nice.
Yeah,
And,
very good.
yeah,
Very intelligent student.
yeah,
I would say.
yeah, very good questions from some students. Very nice. So I am also very thankful to Dr. Shikha for this nice presentation. Actually, any other classes comes, then definitely I will join very earlier. But unfortunately, I am late today. So sorry for that. Thank you, sir, also for your this information. Okay, thank you. Very nice presentation, Shikha. I
Thank
think,
you.
yeah, particularly that question answering session. Okay.
Yes, Dr. Shikha is still the imagination of students. Students of the young class, 8th, 7th classes, etc., coming out so nicely and, seeking clarification on what they want to know and you have done your best in satisfying their thirst, in quenching their thirst. So nice. Thank you very much. It's our
Yeah.
Shikha can be a hub for the later connectivity, maybe.
Yeah.
Thank you.
Yes, sir. So that was a wonderful question answer session. Thank you, ma'am. So now I welcome Niharika to say the vote of thanks. Niharika, are you there?
Yeah, I'm there. I'm audible? Okay. Good evening to everyone. I'm Niharika. I'm studying in 12th standard. So we have a wonderful session with the topic crafting the materials of future, a first principle approach. And I'm very excited to this topic. And Dr. Shikha ma'am done it very perfectly. And the excitement become the truth in this session. That I noticed that from the beginning she start with her life journey and our dream destiny IIT Delhi, then to the MIT. And I hope that every students become very motivated and get inspired by your beginning and to be like you. I'm also an aspirant, so I'm also motivated. Thank you for this wonderful session. And you start from the basics, then you move to your research topics, then you add up the latest add-on to this topic, and it's a detail about this a topic that makes us very close to this topic. And we can see that question answer session, we can see many of the questions that is related to this and more about it, which shows how you influence us in this topic. And very in my personal side and from the US Space Club, we are very thankful to you. I hope we can get many more opportunities from you, your sessions. Then we are going to we have a host from Department of Physics, University of Calicut, Muhammad Shaheen sir, faculties and authorities. I'm very thankful to them. Then we have our great scientists from the ISRO. Their presence and their valuable times make our session more informative. Then Kuti sir and Shajil sir are over here as the pillars of our session. Thankful to them. And I'm thankful to the whole team of UL Space Club and the students over here who attended the session and make our Q&A session more informative. And I'm very happy that ma'am is also making an interactive session with us, and our doubts are getting cleared, and I hope that every students will be like you from IIT to MIT and great scientists over there. I hope one more session.
More good than me. I'm just very average. I'm not that intelligent.
Yeah, actually, we are like we want to IIT, then we want the scientists. You are like an inspiration. Thank you, ma'am, from the personal side and the US Space Club. Thank you, ma'am.
Yeah, thank you so much.
Thank you.
Thank you.
India.
Yeah, sure. Yeah, for sure. Ask anything. Yeah, I will be happy.
Sajil sir, I just wanted to tell, I think her local time could be 5:30 she would have started, if I'm not wrong, in the early morning. It's really, because it unless you don't have the interest, okay, you'll not be able to, it is that 5:30 is a little bit, and that too this cold season. Anyway, thanks, ma. You have given a wonderful insight into the material science and then kind of things. Thanks.
Thank you to all. Thank you all.
Our webinar quiz link is in the chat box, so everyone can ask it from the participants. Thank you, ma'am, once again.
Thank you. Okay, bye-bye. Take care.